free vortex flow, another is forced vortex flows. So in a free vortex flow, I said that the free vortex flow is a is a type of plain circular vortex flow where the mechanical energy, okay, in the entire flow field it will remain constant. So we came to a conclusion that a free vortex flow, it will be irrotational in nature. Okay, but what happens at the center of a free vortex flow? Even at the center of a free vortex flow, the body behaves, the fluid element, it behaves like a solid body and it starts rotating like a solid body. So this happens only at the center of a free vortex flow, because there we observed that the velocity terms, okay, it tends to infinity. That means we obtain a point of singularity at the center of a free vortex flow. So these were certain important things which you need to remember in case of a free vortex flow. Now let's go to the another type of flow, which is a free vortex, forced vortex flow. So before that, okay, one more thing. I just showed you one video where they realized, where they conceived this free vortex flow in a cylinder. So they took a cylinder, at the bottom of that cylinder, remember that jar or cylinder, it was full of water, and at the bottom of that they created an orifice, and then they opened that orifice. Okay, now in this way they created a free vortex flow inside that cylinder. So let us see that if you create a free vortex flow in a cylinder, then what will be the first velocity field, then after that what will be the, let's say, this thing, the pressure distribution, and what will be the energy distribution. So it's obvious that the energy distribution and pressure distribution, they will be given by the same relationships as in the case of a free vortex flow. Okay, but let's see what happens if we conceive this free vortex flow in a cylinder. Okay, so if you conceive this free vortex flow in a cylinder, okay, if you realize this free vortex flow in a cylindrical coordinate system, okay, in a cylinder, such that the z axis you have inclined vertically upwards. So then we call such kind of flow as cylindrical free vortex flow. So there is nothing. The only thing you have to remember that in this case, what we are doing actually, we are creating the free vortex flow is inside a cylinder, and we are assuming that the central axis, the axis of rotation of the cylinder, will be the z-axis. Simple, nothing else. Now, what happens if you conceive this in a cylinder? If you realize the free vortex flow in a cylinder, then at each cross section, or you can say at each cross section of the cylinder, there exists a planar free vortex motion. That means at this cross section, if you go, so the motion will be a free vortex motion. At this cross section, if you go, the motion will be a free vortex motion. So you can imagine that you have a set of concentric lines, concentric streamlines on this plane, then you have another set of concentric streamlines on this plane, and this way it will go around along the z-axis. Okay. So this is a cylindrical free vortex flow. Now, what happens? We already know the total energy at a point remains constant. We already know this thing, that if you go to a particular cross section, then the total energy at a particular point, okay, either along the streamline, that means if you move in a plane perpendicular to the plane of this PowerPoint presentation, okay, then also the mechanical energy is going to remain constant. Or even if you take 2 points here, let's say 1 and 2, then also the mechanical energy is going to remain constant. Okay, so now we means all the things, they remain the same. The only thing is that we are okay discussing this in context to a cylinder. If we take water in a cylinder and if we drill hole at the bottom of the cylinder to create this such kind of, let's say, free vortex flow. Now the equation for energy distribution, it is very obvious that this will be given by P by rho g plus C square by 2 square g plus Z is equal to constant. Now I'm interested into this one, that at a particular cross section, what is happening? At a particular cross section, let us observe the pressure distribution along the radius. So at a particular cross section, you can observe here the Z term, it will remain constant. The Z term is going to remain constant. And then again, this term, okay, you have to nothing, you have to do nothing. You have to put here Z is as constant. Okay, so some constant, now take the Z on the right hand side. So some constant minus Z, that will be again a new constant. So ultimately what we have at a particular cross section, the pressure distribution is given by simply by this relation, that is P by rho plus C square divided by 2R square is equal to C1. So if you remember, even when I discussed in context to a free vortex flow, so if you remember there, we said, okay, if we have 2 points and we know that the mechanical energy is going to remain constant, that means the Bernoulli's equation is applicable here, okay, for a free vortex flow. So we simply put P1 by rho g, okay, plus P1 square by 2g, okay, plus Z1 is equal to P2 by rho g plus V2 square by 2g, okay, plus Z2. So now we are saying that, okay, Z1 will remain equal to Z2. So finally the pressure distribution, if you have to find out, let's say between 2 points, so simply it is given by this one, V2 square minus V1 square. Very easy, nothing else. Now pressure distribution along the Z axis, this is important. This is important. So I just said that the total energy at the point remains constant and it is given by this. Okay. So now let us think about this. That okay. Now right now, just now, I said that okay, if we take a particular cross section, so if we move okay along this line, let's say along a plane, along a circular plane, okay, parallel to the PowerPoint presentation, and if we move along a circular, let's say streamline in a plane perpendicular to this PowerPoint presentation. So in both the cases, I said the total energy which is going to remain constant. But now let us see this, that what is going to happen if the pressure distribution along the Z axis. Okay, that means what is going to happen if we are going to move from this cross section to this cross section. Okay, so let us see this. Okay, so now pressure distribution along the Z axis. So let us say that for some time I'm assuming that along the Z axis this P is going to remain constant. Okay, so along the Z axis this P is going to remain constant. Now if I assume this, then what will happen? We will find out that this equation, it is going to reduce to a new equation because this is constant. Now if you take, let's say, this equation on this side, okay, then what is going to happen? The equation will be simply C square divided by 2R square plus GZ is equal to C1. So just keep this thing in mind, that what I am interested here, actually here I am interested to find out the shape of surfaces of fluid element in free vortex. Okay, for constant pressure. So this is my interest. I'm interested to find out this one. So why this is important, you will come to know. So along the Z axis, first of all, I am assuming, let's say the pressure is going to remain constant. Then if you go to this equation, you will find out that it is simply C square divided by 2R square plus GZ is equal to something new constant C1. Now what is this equation? This equation is simply the equation for surfaces of equal pressure. So this equation, it will represent the surfaces with equal pressure, because see here, this Z term is nothing, just term, it is representing the distance, or let's say the variation in pressure along the Z axis, nothing else. So along the Z axis, since I'm assuming P as constant, okay, so this Z is going to give me the surface of the free shape. Okay, sorry, I'm sorry, the shape of the surfaces, okay, where the pressure is going to remain constant, or where the pressure is going to remain equal. So now can you just tell me that what is this equation? Is this the equation of a parabola? Is this the equation of something like this? or this is a linear equation? What is it? Okay, so let me tell you this one. Z, let us solve this equation further. So Z is equal to 1 by G, okay, then that is C1 minus C square by 2 R square. Now just imagine this at R equal to 0. Okay, if this is 0, then this is tending to infinity. That is tending to infinity, let's say. Then at, let's say, R is equal to 1. Okay, so Z is equal to some value. Here it will get some value, let's say 1 by G. Then R is 1. Then it will be something, let's say C1 minus C square by 2. Then let's say R is equal to 2. So see, this, when you put R equal to 2, so this will become 4. So it will C1 minus C square by 4. That means this term will increase with increase in R. This term will increase. That means if this term is going to increase, then this net term is going to decrease with respect to R. Okay. So if R is increasing, the value of Z is decreasing. So just tell me, like, whether you are you will get a linear surface here or you will get a curved surface here.
Curved surface.
So it is actually basically it will represent, let's say, something like the equation of parabola. So we have, let's say, y equal to x square, something like that. We have y equal to ax square, the equation of parabola. So it is nothing. It is z is equal to some constant times of r square. So now the surfaces of equal pressure in a cylindrical coordinate system, it will look something like this. So you can see these surfaces. Okay, so you can very easily see these surfaces. So now these surfaces, okay, these lines which you are seeing here, okay, which I have drawn here, these lines, these dotted lines, then this solid line, all these lines are what? All these lines are simply the lines of, okay, constant pressure. So since I have plotted it into a 2D plane, that's why I am saying that these are lines of constant pressure. But if you take a three-dimensional view, then that is basically that line, it represents a surface. So you can say these are the surfaces where the pressure is going to remain constant along the z-axis. So that means if you take a point here, if you take a point here, if you take a point here, or if you take a point here, also all the, at all the points, okay, the pressure is going to remain constant. Similarly, you can draw other constant lines for different values of r. Okay, so this is, let's say, r1. Then you calculated z for this r1. Okay, then this is your r2. Then you calculated z for this radius r2. So at different radius, you can get different lines where the pressure is going to remain constant. So this is one very important property of cylindrical vortex flow. Okay. Now I would like to mention one more important thing here, that what is going to happen if the pressure is going to be zero. So let us say in this equation, I just made this pressure as zero. Okay. So then in that case, whatever the value of z which we are getting, see, first of all, make this thing very clear. So pressure is zero, or you can say if this P is P atmospheric. So if we talk of gauge pressure, then we simply say, okay, that we are taking the gauge pressure as zero. But basically here it is representing that if we take the pressure as atmospheric pressure, so in that case, what happened? Is this equation going to change? Anyone? Will there be any change in equation? So I'm just saying that I'm considering, okay, here I just said that P is going to remain constant. I don't care whether this P, it is in the bulk of fluid, or this P we are taking on the surface. I'm not considering that. I'm just saying here that P is going to remain constant in this case. But now let's just take a special case where this P is going to be the atmospheric pressure. So in this case, just tell me, will there be any change in this equation? Anyone?
No, sir.
So there is no change into equation. The only thing is, The only thing is the value of this constant may change. So right now, let's say it is C1, then it could become C2 or some, let's say A, B or some D constant. Okay. So the value of this constant on the right hand side is just going to change. The remaining things, they are going to remain the same. Okay. So now let us talk this thing that then why I'm talking about this, that okay, where P is P going to represent the P atmospheric. So basically at this situation, if the P value is equal to P atmospheric, then in this situation, always remember the value of Z, the value of Z, it will give you the free surface. Okay? That means in this situation, if you calculate this value of Z, then you will come to the free surface. So now this is your, this line which you are seeing, this is your free surface. Okay. So here also you can find out that now at the free surface, these are the lines of this solid one. These are the lines of constant pressure. So till now you will find that, okay, these are almost straight till up to certain extent. Then after that, when they are very much close to the surface, then they will simply become flat like this, nothing else. So like this, they will become flat and this will be your free surface. Okay. So I hope now this is clear to all of you. So we are doing nothing. We are just taking, we are just realizing this free vortex motion in a cylindrical coordinate system, and we are taking, okay, in simple words, that okay, a jar of water you have, and then you are, okay, then you are actually drilling a hole at the bottom of that beaker, and you are creating a free vortex flow inside a cylinder. So these are certain situations. Now let us move to force vortex flow. What happens in a force vortex flow? Now very important here. First of all, just tell me, so what do you think by its name that this force vortex flow, so by its name, what do you think that in a free vortex flow, will the mechanical energy is going to remain constant? So see, it is a force vortex flow. So first of all, okay, just tell me, will there be any addition of energy or dissipation of energy in, let's say, in a flow field of a force vortex flow? Is the question clear? So I am just asking, in a force vortex flow, will there be any addition or dissipation of energy? So like in a free vortex flow, I said there will be no addition of energy and no dissipation of energy in a free vortex flow. But what is going to happen in a force vortex flow?
Addition of energy.
Very good. So addition of energy will be there. Okay. So by its name, it is very clear that here now we are supplying energy from an outside source to create a force vortex flow. Okay. That's why it is named as force vortex, because we are creating the vortex motion. Okay. So what is a vortex motion? Vortex motion is, always remember that a vortex motion is a kind of motion where the streamlines will be concentric circles, nothing else. Okay. So now free means that we are not giving any energy from an outside source to create the vortex motion. And force vortex, that means we are giving energy from an outside source to create the vortex motion, nothing else. So now the flows where the streamlines are concentric circles, and this is very important, that how a free vortex flow is different from a force vortex flows, that here the tangential velocity, this tangential velocity, it is directly proportional to the radius of curvature. Okay. So in a free vortex flow, if you remember, in a free vortex flow, what was the velocity field? Just tell me quickly. Vr was equal to 0. That means there was no velocity in the radial direction. And v theta was
P by R.
P by r. So here we observed that this v theta tangential velocity, it is inversely proportional to radius. Okay. Now in a force vortex flow, this equation will be different. So in a force vortex flow, we simply say that this v theta is equal to simply omega into r. Okay. So this is the case for a force vortex flow. So in a force vortex flow, the tangential velocity, it is directly proportional to this radius, and it is given by simply r omega, nothing else. So This is the key difference. So always remember that sometimes it happens that whenever somebody asks you the key difference between a free and forced vortex flow. So in many books you will find that they simply define in this way, that in a free vortex flow, okay, it is a kind of flow where the tangential velocity, it is inversely proportional to radius, and in a forced vortex flow, it is a type of flow where the tangential velocity is directly proportional. So somewhere you will not find like this much discussion. This just limited to this one, and after once you define the flow field, then everything comes automatically. Okay, so now let's talk of vorticity. So if you remember that the formula for vorticity in a cylindrical coordinate system, I use this formula delta v theta by delta r, okay, minus 1 by r delta vr by delta theta plus v theta by r. Okay, so I would like to, okay, ask you people, just try to find out the derivation for vorticity, okay, in a cylindrical coordinate system. Just go through this, and if you don't get it, so this is available in Som and Vishwas book. So if you don't get it, then just ask me. Okay, so in a cylindrical coordinate system, right now you just have to see this equation, that the vorticity, it is given by delta v theta by delta r minus 1 by r delta vr by delta theta plus v theta by r. So why are we always calculating the vorticity? Can anyone tell why are we always calculating the vorticity? So if you remember, what is this? Delta cross v vector is equal to 0. That means the flow is rotational or irrotational?
Irrotational.
Rotational.
Irrotation.
Vorticity is what? Vorticity is nothing. Generally, the formula for vorticity is given by this. Okay. So we are basically calculating the vorticity just to figure out whether the flow is rotational or irrotational, nothing else. So this is the reason for calculating vorticity. Now let us see this. Then just put the value of v theta from here into here. So v theta is r omega delta by delta r of v omega r. That means this r is going to cancel out. The only term that will be left is omega. Then minus 1 by r delta vr by delta theta. So vr is already 0. Okay. Now coming to this term, so v theta is r omega. So again you have omega here. Okay. So finally the vorticity will be omega plus minus 0 plus omega. So vorticity is equal to 2 times of omega. So just tell me now. Now is the flow irrotational or rotational?
Rotation.
Rotational.
In this case, the
Rotational.
flow is rotational, because now your vorticity term, it is having some value. Okay, and never get confused between a Cartesian and cylindrical coordinate system. Both are same. If you take a Cartesian coordinate system also for calculating vorticity in this case, okay, then also you will get the same result. So why are we considering actually this cylindrical coordinate? Because since we are assuming everything that, okay, every fluid element, it is moving in a circular path. So the cylindrical coordinate system in this case, it becomes an easy way for analysis, nothing else. But you can do the same analysis using a Cartesian coordinate system as well. Okay. So now we have this vorticity as 2 omega. That means the flow is rotational flow. So a very important point I'm going to mention here, that a forced vortex motion, it is not irrotational. Got it? Rather, it is a rotational flow with a constant vorticity 2 omega. Very, very important thing. So now this another important point, that means all fluid particles rotate with the same angular velocity omega, like a solid body. Okay. So this important point you have to remember, that in a free vortex flow, the fluid particles, they were not behaving like a solid body. Okay, the flow was irrotational, and all the fluid particles, they possess different angular velocities. Okay, so the flow, you can say there that the flow was pure shear deformation in case of a free vortex flow. Okay, so when rotation is absent, then we simply say that, okay, this is going to deform. Okay, so we already know the fluid elements, they deform, right? So in a free vortex flow, the fluid element is going to deform into pure shear. Okay, so there will be no rotational component there. But here, what is going to happen? Here, this is very important, that here your fluid particles, they will not deform, okay, under the action of shear stresses. That means if you place a, let's say this is your force vortex flow, and in this flow what you did, you just placed a rectangular element like this, okay, or let's say you created uh, a rectangular shape using matchsticks, and you just drop this matchsticks in. So what is going to happen? Now you will find this is not going to deform. It will behave like a solid body. Okay. Or if you place a matchstick here, it is going to rotate like this. Okay. So there will be no deformation. There will be no spinning of this around its own axis. It will simply rotate like this. Okay. So very important point here. So all fluid particles, very important, they rotate with the same angular velocity and they behave like a solid body. So that's why we call this force vortex flow as a solid body rotation. Very important thing. Okay, so we term this force vortex flow as a solid body rotation. And here I would suggest all of you to go through the video which I showed you, okay, which I showed you, let's say the vorticity video and the rotational and irrotational flow video. So that video will make the things more clear. Go through that video once again. Okay, so check the video. Now let's move to pressure distribution along the radius. In this case, what will be the situation? What will be the pressure distribution along the radius? So now again, for this case, if you remember that we have this equation. Okay, if you remember in the last session, we use this equation again, the Euler equation of motion. Either you derive it through the Euler equation of motion, or you simply use the energy equation. So if you remember the last session, so now again I am taking the Euler equation of motion. So if you remember the Euler equation of motion along the radius, it is given by 1 by rho dp by dr is equal to v theta square by r minus g dz by dr. Okay. Now we have to find out the pressure distribution along the radius. So what we should do after that? What is the next step? What we did in case of free vortex flow?
Multiplying by dr and then integrating it.
Okay, so very good, very obvious. Simply multiply it with dr and just integrate it. And okay, in the radial direction, that means you have these two concentric lines. So along this radius, you have taken only 2 points, 1 and 2. So you are interested to find out the difference in pressure between these 2 points. So this is very much similar to what we did in case of a free vortex flow. So we are deriving the equation of motion using the pressure distribution using the Euler equation of motion. You can simply do it by using the energy equation as well. Okay, so for energy equation, you can try yourself. Now just tell me one thing here, very important thing. So for a free vortex flow, I was writing the equation like this, that okay, P1 by rho g plus V theta 1 square by 2g plus Z1. This is equal to P2 by rho g plus V theta 2 square by 2g plus Z2. So I was writing the equation like this for a free vortex flow, because there the Bernoulli's equation, it was valid throughout the entire flow field. Okay, so it doesn't matter you are moving along the streamline or in a direction, okay, in a direction normal to the streamline. So we will see that in the particular plane, the mechanical energy, it is going to remain constant. So just tell me this thing here, very important, that is this equation going to remain the same for a force vortex flow also? Think about that. Is this equation going to remain the same for a force vortex flow? Okay, so let's take
Sir,
one.
we have to. I think we have to add the work head.
Add the 1/3.
Work done by the machine.
Okay, so that is there. One thing is there. Very good. So that is already there. But right now my question is that just tell me. So is this equation applicable for a force vortex flow also?
Sir, in that Z1 would be equal to Z2.
No, these are those the datum. Okay, then let me start from the very basics. For a force vortex flow, what I said, the flow will be rotational flow. Okay, so first of all, just tell me. So if I am moving along, let's say the streamline. Okay, so I am moving along the streamline, and I am saying the flow is steady. The flow is steady, incompressible, and invisible. So if this is the situation, then we all know that if we move along the streamline, then the mechanical energy is going to remain constant. Okay. But I said I proved one situation that if the flow is irrotational, then the mechanical energy, that means besides steady, incompressible, inviscid, and if we add one more thing, that the flow is irrotational also. Okay. Then we said that it doesn't matter where are you, at what point you are in a particular flow field. So it is going to remain constant either along the streamline or along the radius. Anywhere in the flow field, it is going to remain constant, the mechanical energy, correct? So my simple question is, here I just said that your flow is not irrotational. It is a rotational flow. The fluid particles, they are behaving like a solid body. So first of all, just tell me, will the Bernoulli equation hold valid in this case? If we go along the radius,
No, sir.
No, sir.
so very clear. So if the Bernoulli's equation is not valid, then will this equation be applicable if, let's say, we move in a direction along the radius? Okay. So why? Why? Because we are interested in this one, pressure distribution along the radius. We already know the pressure distribution along the streamline. There you can simply apply the Bernoulli equation. If given that the flow is steady, incompressible, and invisible. But what along the radius? So that means if Bernoulli's equation is not valid along the radius, okay, why? Because the flow is rotational. So it is very obvious that if the flow is rotational flow, then the Bernoulli's equation, it will not be applicable along the radius. So that means this equation is not valid for a force vortex flow. Okay, and the given that we are talking along the radius, we are talking the let's say energy distribution between 2 points 1 and 2 along the radius. Clear? Now if this is the situation, then that means the pressure distribution in this case, it has to be different from the one which we consider in a case of free vortex flow. So now simply what you do, you simply integrate this integration. Okay, so now you can simply see here that it will be, if you integrate this, then it will be P2 minus P1 by rho. That means this 1 to 2. So 1 by rho, that means if we consider the flow to be incompressible, so 1 by rho we can take outside, dr will cancel out. So dp is simply P2 minus P1. Now this is 1 to 2. Now in place of V theta, you just put R square omega square, correct? So we substituted R square omega square divided by R dr minus G Z2 minus Z1. Here many students, they do the mistake. Okay, always remember that you don't just integrate V theta directly, that you took V theta square outside and you integrated 1 by R dr. Okay, because V theta is already a function of R. So this is a special property of, okay, a plane circular vortex flow. Even if you go to a free vortex flow, this V theta is inversely proportional to R. If you go to a forced vortex flow, this V theta is directly proportional to R. So you have to keep this thing in mind, that this V theta is a function of R. It cannot be taken outside. So you have to put the value of V theta as R omega. And if you deriving this equation for a free vortex flow, then just simply put V theta is equal to C by R. Very easy. Okay. Now you just integrate it. Finally, you will get this equation, omega square R2 square minus R1 square divided by 2 minus G Z2 minus Z1. So very important thing, see, I am going to mention here. Here, see here, in this equation, if you, let's say, arrange these terms in a way similar to Bernoulli's equation. Okay, we are arranging this term in a way similar to Bernoulli's equation, then we will get this P1 by rho. Okay, or if you divide by G, then P1 by rho G. So that is another thing. So it is P1 by rho minus, what is this? Omega square R1 square. What is this? Just tell me.
Rotational energy.
Okay,
V
so
theta
this is
square.
nothing.
V
This is your
theta
V theta 1 square by 2,
Mhm.
right? Plus G Z1. This is equal to P2 by rho plus V theta 2 square by 2. Okay. Plus G2. Okay. So tangential velocity at point 1, tangential velocity at point 2. So this is velocity head at point 1, velocity head at point 2. So very important thing. What is the difference you noted here? If
Sir, on
we
the one side it is minus V theta 1 square by 2, and on the
very
other side it is
interesting thing
plus.
here. Now you observe here that on one side this is a minus term, right? And on the another side this is a positive term. So you have to keep this in mind that this is not Bernoulli's equation. So I have specifically mentioned this thing here because many times the students they get confused. They think, okay, this is also Bernoulli's equation. Bernoulli's equation is valid only for an ideal flow. That means if the flow is okay, the flow is steady, incompressible, inviscid, and irrotational. Okay. So very, or if you remove the irrotational term, then this will be valid only when we move along the streamline. So see, very important conclusion we came here that now just tell me that I have one point here and another point here, one or two. So first of all, let's go one by one. First of all, just tell me the angular velocity. Let's say one element is O1, another element is O2. So first of all, just tell me which element O1 or O2 it is going to rotate at a high angular velocity.
O2.
O2 will rotate at a high angular velocity because it is very obvious because V is now directly proportional to radius. And if you remember the case of a free vortex flow, there the situation was reverse. There O1 was rotating at a high angular velocity. Right? So, am I correct? Okay, let me see.
Yes, sir.
Yes, sir.
R. So R2, okay, it's correct. So omega O2 is going to rotate at a high angular velocity. Okay, so this is one thing. Now, just tell me that can you imagine this? Are you able to imagine this? Let's say you take water in a glass. Just imagine at your home, and if let's say sometimes you shake that glass, correct? So if you observe that the outside, the water layer on the outside, it rotates with a high angular velocity. Just try to imagine this thing. This is actually applicable in practical situations as well. And if you remember the case of a free vortex flow, in a free vortex flow, we already observe that if the water is passing through a hole in the wash basin, we observe that the water layer on the outside. Okay, try to imagine this. The water layer on the outside, it moves slightly slowly as compared to the water layers on the inside. Okay, so this is very beautiful equation. It will give you a real actually picture of that situation. Okay, so now this is one point. Now just tell me that if the angular velocity is high at point 2 as compared to point 1. So just tell me at what point you feel the energy is low. At point 1 energy is low or at point 2 the mechanical energy is low.
Sir, the point where the radius would be higher, there the energy would be greater.
Right. So here very obvious that at point 2 the energy will be greater. Okay. Because here also we are saying that we are subtracting at point 1. If you observe, we are subtracting this term minus V theta 1 square by 2. Okay. So it is very obvious that the energy at point 2 will be greater. Now let's say, and okay, we are coming to this energy distribution as well. So let's see this. So now the mechanical energy distribution along the radius between 2 points 1 and 2. Okay. So if you go to again to the previous equation, so along the radius, we actually derived this equation. Just remember. So dH by dr, V theta by G, dV theta by dr plus V theta by R. Okay. Now this is going to be equal to simply put the value of V theta R omega. So R omega here divided by G, and d by dr of R omega is omega plus this is again omega. So here it will be simply 2 omega square divided by G. So you can simply derive this, very important. So now dH by dr is equal to 2 omega square by G. So let's see the energy distribution as well. So it is very obvious now. Now you have to multiply this with dr and just integrate it between 1 and 2. Okay, so finally you will get this energy distribution. Very easy, that integrating this S2 minus H1 will be equal to omega square by G R2 square minus R1. So this term on the right hand side, it will always be positive term. Okay, so we can say that H2, the energy at point 2, it will be greater than the energy at point 1. Now check it for a free vortex flow. So just go home and try to check it for a free vortex flow and try to make some clear differences between these free and forced vortex flow. This is very important phenomena in our day-to-day life. So now alternative distribution is also there. Alternative distribution is obviously very easy. So you can simply take H2 minus S1. So what is this H2? H2 we all know that P2 by rho G, okay, plus V theta 2 square by 2G plus G Z1. Okay, and what is H1? H1 is P1 by rho G plus V theta of 1 square by 2G plus GZ2. Okay, so this is our mechanical energy. Always remember, okay, the Bernoulli's equation, it only defines whether there's mechanical energy is going to remain constant or not. But if somebody asks you what is the total mechanical energy, then this is our total mechanical energy. Finally, what you do, if you have to directly find out the distribution of radius, simply subtract these two. H2 minus H1 is equal to P2 minus P1 by rho G plus V theta is 2 square minus V theta 1 square by 2G. Now you already know the value of P2 minus P1 by rho G. You can put it here, okay, and you can find out this energy difference. And you can go in the reverse way as well. So you know the energy, you put it here, you can find out the pressure difference. Okay, so very important thing. Yes, anything?
Sir, here you have written that check it for free vortex flow, but for free vortex flow, we take dH by dr as 0. Then what will be the equation?
Okay, so very good. So that means if dH by dr for a free vortex flow
Mechanical
is,
energy will be constant in that.
yeah, so H will be constant, nothing else. So
Okay.
that's what. So very good. So there will be no actually variation in energy. And check that pressure difference, this equation as well. Compare it with, very good, very good. I appreciate if you remember this. Okay. So now the pressure difference equation, compare this also. Compare this also with free vortex flow and try to find out the difference. So it's very easy. Here it is omega square by 2 R2 square minus R1. There just try to check what was the equation. Okay. So I will leave it to you. Now let's move to cylindrical force vortex. So there is actually a spiral one also. Spiral free vortex and a spiral force vortex. So if you are interested, you can go those ones. But I will limit myself to cylindrical ones only. Okay. So again, a cylindrical force vortex motion, it is realized in a cylindrical coordinate system. Okay, so very easy. So it is cylindrical force vortex motion. It is realized in a cylindrical coordinate system. Again, where at each horizontal cross section there exists a free vortex flow. That means again we are taking a cylinder. We are actually now filling this cylinder with water. And let's say if we provide a handle or a small shaft, okay, at the end of this cylinder, and we provide a rotation to this cylinder. Okay, so here I'm mentioning very important thing. Always remember that now there will be the supply of energy from an outside source in case of a force vortex flow. Okay, so we are now rotating this cylinder. Now the water inside this, the fluid elements inside this, they will create a force vortex flow at each cross section. So if you go to this cross section, this cross section, this cross section, at every cross section you will find that the flow is a force vortex flow. Okay, so now again we will do the same thing, nothing else. So if you have to take, let's say for 2 points 1 and 2 on the same horizontal plane, what is the pressure difference? Okay, so this will be the pressure difference. Okay, now very important thing, again I am interested to find out the shape of free surface. If any free surface is existing in a fluid flow, so what will be the shape of that free surface? So let's say if this point 1, it lies on the axis of rotation, and point 2 is at a radius r from the axis of rotation. So this is my point 1. Let us say this is my point 1, and this is my point 2, which is at a radius of r. So in this situation, what will happen? In this situation, you will simply have this equation that, okay, P2 minus P1 by rho G, that is equal to omega square r square divided by 2G. Now, what is this P2 by rho G? Okay, What is this P2 by rho g? This is nothing. This is the pressure head. Pressure head, that means you can simply call this the depth below the free surface. Depth below the free surface. Okay. So finally, nothing else. You are just taking this P2 minus P1 by rho g omega square divided into R square divided by 2g. So basically, we are talking at a constant Z. Okay. So this value of R, the value of R, okay, if you calculate this in terms of this pressure, okay, then this value of R, or you can simply say this equation, it represents a paraboloid of revolution. Paraboloid of revolution. That means here the free surface will be a paraboloid. Okay, the free surface will be a paraboloid. So if you take the shape of free surface, so in this case the free surface will look like this. Okay, so it is paraboloid of revolution. So this is the shape of a paraboloid. But if you go for a free vortex flow, there you see, you observe that in a free vortex flow, if you go, then the equations of constant pressure are like this. Equations of constant pressure like this, and your free surface was something like this. Okay, so this was your free surface. Okay, okay, so it is almost horizontal. Your free surface is almost horizontal except around this center. Okay, so we have already observed. If you observe that video very carefully, then you will find that in a free vortex flow, the this thing is always horizontal. Only at the center you start feeling that okay, the fluid layers, they are going inside. Okay, is this picture clear to your mind or not?
Yes,
Can
sir.
you, are you able to imagine this? See, in a free vortex flow, we always observe that everything is going, okay, through this, through a hole at the center. Everything is, all the fluid is trying to pass through the hole at the center. And if you observe the surfaces, okay, this is very beautiful thing. So if you observe the surfaces, they are almost straight, except at the center, you will feel like that, okay, all the fluid layers now they are going inside. But if you create a force vortex flow, then the situation is just opposite. The situation is just opposite. Here you have the paraboloids. The shape of free surface will be a paraboloid. It is not going to remain straight like this. Okay. So now here you will not feel this, that okay, all the fluid is trying to move to the center. Instead, what you will feel? Just tell me.
Sir, will it behave like a centrifugal force?
Right. So here you are feeling that all the fluid layers, they are trying to move towards the center. But in a force vortex flow, you will feel that all the fluid layers, they are trying to move towards the center or away from the center.
Away from the center.
So very clear. So here you will feel, observe that all the fluid elements, they are trying to actually move away from the center. So that is one of the beauty, that when we create this force vortex flow from an outside energy source. Okay. So now such a flow field can be generated by rotating a cylindrical vessel containing a fluid. And very important point I am going to mention here, that energy is transferred from an outside source to the system. So now after this, just very important thing I'm going to mention, that let's say if I said, am I providing any torque in this case or not? So am I providing any torque?
Yes, sir.
Yes,
Yes,
so
sir.
yes, I am giving a torque basically. Okay, the torque to rotate this. Okay, this force free and force vortex flow. So one thing I have never discussed with all of you, I will come to that as well later on. But I would advise that try to figure out what about momentum. We talked about energy, we talked about force. What about momentum? Will the angular momentum is going to remain conserved or not? Just think about this. So for a free vortex flow, whether the momentum will be conserved, or for a force vortex flow, whether the momentum will be conserved. So just try to think about this. Okay. So we are talking basically about angular momentum here. Okay. So now let me share you one equation to make my point more clear. One video, sorry. Let me share one video to make my point more clear. Okay. Regarding this thing, the force vortex motion. So see, I am going to show you that how a force vortex motion is created, and basically I am interested to tell you the shape of the surface in case of a force vortex motion. So this is uh, instrument from a company like Decoin. So they provide actually laboratory experiments for, or laboratory equipments for doing all such kind of experiments. Now you can see the beauty of this. It's a very beautiful experiment. Now see here. See, this is your paraboloid of revolution. That means the surface is a paraboloid and this is actually revolving around this center. Okay. So this is very obvious also. If we are rotating something, so if there is some let's say fluid in the container, it will actually tend to fly away from the center and it is going to create a depression at the center basically. Okay. So I think this is clear to all of you. Now let's discuss about an important device that is called as Venturimeter. Okay. So let me create a new presentation here. So first of all, just tell me any doubt till now? Till now, is everything clear to all of you?
Yes, sir.
Okay. So now let's move to another important device that is called as Venturimeter. So this will be the last topic I am covering today. So uh, maybe after this we will go to some other topics as well. Let's say like after this I am planning to actually discuss something about the Reynolds transfer theorem, and after that we will take numericals, a lot of numericals sequentially. So before actually the numerical session, I will ask all of you to actually go through all the equations, all the formulas, so that at the time of solving the numerical you have this thing in mind. Okay, so now let's discuss about this one. So now, first of all, I am talking about flow through a pipe.
Sir, we are not able to see your slide.
Okay, okay, I am sharing. Just give me some minute. Okay, so let me share my slide. I think now it's visible.
Yes.
Okay. So basically here I'm going to discuss with all of you that flow measurement through a pipe. Okay. So measurement of flow through a pipe. Okay. So let's, before going to this, there is also one very important application actually of this one, that Bernoulli's equation. So I would like you go through this yourself. It is very important concept, and in many places this is being used. We call this as hydraulic siphon. Try to figure out this yourself. This is available in Som and Vishwas. That what is a hydraulic siphon? So it is just a very easy concept. So I will simply give you an idea. Sometimes let's say you have one beaker and one beaker at some another height. Okay. Now, what is a hydraulic siphon? Basically, you connect these two through a tube and you create a pressure difference in the tube in such a way, that water, it starts moving from a tank at lower height, to a tank at a higher height. So a Bernoulli's equation plays an important role into this. Okay, so just try to figure out that how does a hydraulic siphon actually does this, that you are able to move water from a tank at lower height to a tank at a higher height, because you can imagine that at a higher height the potential energy will be higher. So we can assuming the energy, it should flow from a higher side to lower side, but it is happening that that we are possible, even if the we means it becomes possible to create the flow of energy from a tank, let's say from a low energy side to a higher energy side. Okay, so just try this yourself. Now let me discuss about Venturimeter. So first of all, what is a Venturimeter? So a Venturimeter, first of all, Venturimeter is a device used to measure the, very simple, measure the flow rate through a pipe, nothing else. Okay. So we use a Venturimeter for this purpose. Okay. Now, what is the construction of a Venturimeter? It is very simple. So first of all, a Venturimeter, if you see, it has a converging nozzle, or you can say you better not say it nozzle. Nozzle is something different. So for nozzle, we only have either a diverging converging portion or a diverging, but here we are going to combine these two. So first of all, in a Venturimeter, you have a converging section, converging conical section, conical section. Okay. Then you have a small length, okay, a small length with straight diameter. That means there is no conical sections, only a pipe, a short pipe you can see. So this portion is called as, very important, this portion is called as throat. This term is very important. So this person we called as throat of the Venturimeter. Okay. Now, again, after this, we have, sorry, we have a comparatively longer diverging section. So this is very important, that your diverging section, okay, this is slightly longer in length as compared to the converging section. So this is my throat and this is my, so very important. So this is converging section, this is your diverging conical section, okay, and then you have the throat. So now we use this Venturimeter to measure the flow rate through a pipe. Now how it is done? Let's understand this, how it is done. Okay. So the this thing is also remember that this is short, the conical portion or the converging conical section, this is short, and the diverging portion of this Venturimeter, it is long. Okay, and these two are connected by a throat. Okay, so now let us discuss for some time that, okay, what will happen. Let's say the fluid is flowing into this direction, so you will install a Venturimeter in a pipe to measure the flow rate in the direction of flow. So remember that this conical section, it should be installed in such a way that okay, water or the fluid will pass first through the short converging conical section, then it will pass through the throat, and then it will go to the diverging conical section. Okay, very important point you have to remember. Now just tell me what will happen. Let's say the flow, it entered at here and it started moving towards this point. Okay, and I am assuming the ideal situation here, that flow is, again, flow is, let's say I'm directly writing down ideal, steady, incompressible and invisible. Now just tell me here that what will happen to the, first of all, let's take the terms one by one. What will happen to the pressure energy or pressure head when the fluid will move from this point to this point?
The pressure will increase. Pressure head will increase.
Pressure head is going to increase. Think about it.
So basically, velocity will increase.
So velocity is going to increase. Very good. So the kinetic head or kinetic energy or velocity head,
Yes.
that's going to
Yes.
increase.
Velocity is going to increase.
So what will happen to pressure then? Pressure energy
Decrease. It will decrease.
It will
decrease. And
decrease.
what about potential energy?
It will remain same because it is on the same
Is on
elevation.
the same level. Now, this is the situation when you move from converging to this portion, okay, to the throat. Now, suddenly, okay, if we move from this, let's say this diverging portion, so what will happen again? Just tell me. So, what is going to happen again? If you move again through this diverging
Velocity, kinetic head will decrease and pressure head will increase. But
kinetic.
sir, but the time taken in the short one would be lesser than in the long one because
Okay, so here what will happen? So here you can see that in this case, when you move through diverging portion, then suddenly what will happen? The pressure energy that is going to start increasing and the kinetic energy that will be going to decrease. Okay, so let me mention one very important point thing. Let's say if I remove this throat, okay, I remove this throat and I just connect these two directly. So what will happen in that case? There will be not a smooth transition of flow from this converging to diverging section. So always remember, we create this throat is there. Okay, so my purpose to discuss this was because see, there's sudden change in energy. Okay, it can create a sudden change in energy. It can create a disruption in flow pattern. Okay, so the flow will become like too much turbulent, or you can say unsteady at the, oh my god, what happened? So the flow can become too much turbulent, or you can say unsteady at the throat. Okay, turbulent, unsteady, or non-uniform, whatever you want to say. So it will become, let's say, very disrupted at the center if we directly convert this converging and diverging section. So throat basically it ensures a smooth transition. Remember this thing. That's why we actually use a throat here. Smooth transition of flow. Okay. Now let us move to next slide. Let us discuss that. Okay, how then this Venturimeter measures the flow rate. Okay. So again, it ensures a smooth transition. And again, one more point I just note down that loss of energy. Definitely, if loss of energy is minimized, note this second point as well. This is also very important. That the purpose of this throat is actually to prevent the loss of energy due to abrupt change in the flow pattern. Okay, so that's what. So now let's move to this one, that how it basically measures the flow rate. So let's say you have a pipe like this. Let's say you have a pipe like this, and in this pipe I want to measure the flow rate. So let's see. Now I installed a Venturimeter into this. See, you can do it for a plane, or you can say you can do it at a constant datum also, but I am taking the inclined one. Okay. So ultimately the result will all almost the same, you will come to know. Now this is my throat portion. Okay, and then after that immediately there will be a diverging portion like this. So this is my Venturimeter. Now let me take 2 points here. Let me take 2 points here. Okay. So let me take, this is my point 1. This is my point number 2. So point number 2 I am taking at the throat. Okay. So point 2 I am taking at the throat. Always remember this thing. So now let us understand this. So what is the flow direction? The flow direction is this one. So definitely now first of all I am interested to, let's say, calculate the velocity at this throat. Okay. I'm interested to calculate the velocity at this throat. So let us take one by one. So let's say this is the distance Z1 from, let's say, any datum, and this is my distance Z2. Okay, let's say from any datum. Now I am already assuming that the flow is, let's say, steady, inviscid, and incompressible. So just tell me quickly how to calculate the velocity at point 2. How to find out the velocity at point 2? What we should do?
Sir, A1 V1 equals to A2 V2.
That is one factor. And if I have to relate it, let's say, with pressure and another things, then
Applying Bernoulli's equation.
Bernoulli's, yes, sir.
Bernoulli's
Bernoulli's
equation.
theorem.
so now I'll simply apply Bernoulli's equation. That is a very important application of Bernoulli's actually. So that is Bernoulli's equation. Now simply it will give you P1 by rho g plus V1 square by 2g, okay, plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2. Finally, you solve this equation and you will get V2 as 1 divided by square root of 1 minus A2 square divided by A1 square. So finally, I am writing down this one. So Bernoulli's equation is this one. Then actually we use continuity equation as well. Okay. So continuity equation, you know that for a steady flow, and if even if the flow is incompressible, we simply say that, okay, right now, if you remove this incompressible term, so you just take a fluid of constant density, because we are measuring the flow of a fluid through a pipe. So generally the fluid density is, let's say, assume it's not going to fluctuate. So it is simply that volume flow rate is going to remain constant. So you can say A1 V1 that is equal to A2 V2 from continuity equation. Okay. Now simply put this one into this thing and you will find out that V2 is equal to 1 divided by square root of 1 minus A2 square by A1 square. Finally, root 2G, very important thing I am going to discuss here. So root 2G, okay. Then here you will get P1 by rho G plus Z1. One term will be this. Another term you will be getting minus 2G, okay, and this will be again P2 by rho G plus Z2. So if you arrange the terms, then you will find this is this thing. Now, can you tell me what is this term? If you remember that in case of an inclined manometer, when I was deriving the equation for an inclined manometer, I gave this term a specific name. Can anyone guess what was that? So I gave this term a specific name. If you remember, when I discussed this for, let's say, inclined, sorry, not an inclined. I'm sorry, not an inclined. An inclined. Let's say if I'm going to use a differential manometer. Sorry, I'm sorry. In a differential manometer in a inclined pipe. Can anyone remember? Here we took this difference as delta Z, and we said, okay, this is your Z1 something, this is your Z2 something. So we call this term as piezometric head or piezometric pressure. If you remember that we took this term P1 plus rho G Z1, okay, minus P2 plus rho G Z2. That was what? Piezometric pressure. And for a differential manometer, we always know that P1 minus P2 is nothing. This is what? This is simply the difference between rho G H1 minus H2. So if the pipe is straight, then we say this H1 minus H2 is, let's say, simple the heights. Okay. But if this is not straight, then we call this as piezometric height. Okay. So if you remember there, then generally we can give this equation as 1 by square root of 1 minus 1 minus A2 square divided by A1 square, and we will simply call this as 2G H1 star minus H2 star. So what is this H1 H2 star? That is H1 star comma H2 star. They are known as piezometric heads. Now you have to remember that this piezometric head, it is a combination of pressure head and potential head. Always remember, keep this in mind. Okay, so piezometric head at points 1 and 2. That means you are considering the potential energy and the pressure energy both. Okay, so that is called as piezometric head. Now let's move to the discharge. So what will be the volume flow rate? Volume flow rate will be nothing. Volume flow rate will be simply now Q is equal to, okay, A2 V2. So finally Q, you will have A2 divided by square root of 1 minus A2 square divided by A1 square multiplied by root 2G H1 star minus H2 star. Very simple. Okay, so this is the discharge or flow rate through a pipe. And now very important thing I'm going to mention here. Let me do one thing. Let me install a manometer between these 2 points. So this is my point 1, and let's say this is my throat. This is my throat area. Okay, so now let me do one thing, that let me install a manometer at the throat, and let us fill this manometer with a manometric fluid rho m. So finally you remember that you can express this equation in other terms also. So if you remember that from manometric equation, now I'm not going into the details of this. You are mature enough to figure out this, that from manometric equation, if you remember, when I derived the manometric equation for inclined plane, so you can simply say H1 star minus H2 star. It is given by rho m by rho minus 1 multiplied by delta H. Okay. So what is this delta H? This delta H is simply this distance. Okay. So this distance is your delta H. Okay. Very easy. Okay. So now this is clear to all of you, I think. So manometric equation, you already know that if you put a manometer there, we can simply use, let's say, move from one side of this manometer and go to another side and try to figure out this equation. It is very easy. Now finally you put this equation into this term, okay, and you get this relation as A1 A2, okay, divided by square root of A1 square minus A2 square multiplied by root 2G rho m divided by rho minus 1 into delta H. So finally, if you want to measure the flow rate through a pipe, you should know only what? The area, the cross-sectional area at the converging section and at the throat, A1, A2. Okay, then finally, okay, always remember that this is your A1 and this is your A2. Okay, so this is the cross-sectional area at point 1. This is the cross-sectional area at point 2. Finally, you will have this A1, A2 divided by square root of A1 square minus A2 square root 2G. Now you have to just know the density of fluid and the density of manometric fluid. So the density of fluid in the pipe and the density of manometric fluid, and you should know this. Okay, you install a pressure meter, okay, or a differential manometer at this point. Just measure this difference and find out the flow rate. Now, very important thing I am going to mention here. Just remember. So now, very important thing I am going to mention here. See, this delta H, it is independent whether your pipe is inclined or straight. So this is one point I want to mention, that this is independent whether your pipe is inclined or it is straight. It doesn't matter. Okay. So we proved this, though it is H1 star minus H2 star, but finally if you take the manometric equation, then this H1 star minus H2 star, okay, it is simply equal to rho m by rho minus 1 into delta H. So try this manometric equation yourself. Okay, we have already derived this in very previous lectures. Now, very important thing, due to loss of energy at the throat, in the form of flow separation. So I will discuss this flow separation later on, that sometimes it happens that there is separation of flow at throat. Okay, that means at throat, the fluid layers, they will try to fly away from the walls of the pipe. Okay, so they will tend to move away from the walls pipe. So that is called as flow separation. We will discuss this later on. So due to this, there is loss of energy, and then we have the actual discharge or actual flow rate CD multiplied by, okay, this term Q. So Q actual is CD multiplied by Q theoretical. Okay, so this is the actual equation in the actual situations, and CD, the coefficient, it will depend upon the design of venturimeter or shape of venturimeter, or you can simply say shape of thought. And now just tell me one thing, the value of CD should be less than 1 or greater than 1? Just tell me quickly. We don't have now
Greater
that
than one.
Less
Greater
than
than one.
1.
will be less than 1, because the actual flow rate, it will always be less, okay, compared to the theoretical, because we are not considering the loss of energy, the flow separation, the disruption in flow, all those things we are not considering. So this will be less than the theoretical, so that means the value of CD is less than 1, and it generally lies between 0.95 to 0.98. And what is this CD? This CD is called as coefficient of discharge. So there are many other applications of this one. There are many other applications, okay, of this thing. But right now, just I will discuss venturimeter. Then you have orifice meter and many other. So this you can see yourself. Okay.
Sir,
So there are those,
we are considering that to find the theoretical, we are considering that the fluid is in viscid.
right,
And
right, right. But in actual, it is not possible.
yes,
Right,
sir, in actual, there would be contact between the pipe and the fluid.
right, right, right. So that's why, because of that, we are doing this. So now let me end this meeting then. I think today I took a lot of time, but next few lectures will be like this only. So just be prepared, because we are uh, lacking in terms of syllabus too much. Okay.
Sir,
Yeah.
sir, what is the deadline for assignment?
Okay, assignment 3, the which you have taken. First of all, you don't need to, let's say, a very in-depth analysis. You have to just prepare one page report for that. Okay, and one student asked, okay, do we need to discuss, okay, fluid mechanics, what happened during lockdown? So I will exactly tell you. You have to discuss the role of fluid mechanics in transmission of, let's say, COVID-19. So just try to figure out that if somebody coughed or sneezed, so those droplets, they are suspended in the air. So how are they affected by, let's say, fluid dynamics, that is turbulence, surface tension? So do these factors have any role? So you have to figure out this. So you can discuss, but try not to keep the same material. Okay, try to keep a variation in different material, and then just make a one-page report. And for deadline, I am not keeping any deadline for this assignment. Okay, so I will tell you, maybe at the end of November, I will give a deadline. For this, you can take your time, because this assignment is maybe slightly complex for you. But you got what you have to do into that assignment. Is this clear to all of you?
Yes,
Yes.
sir.
Okay, so you have to actually talk in terms of from a mechanical engineering or fluid mechanics point of view, that will this fluid mechanics, it will affect the transmission of COVID-19 or not. So that is my point. So go through those research papers, browse internet, find some articles, and try to figure out. Okay, anything else?
No, sir.
Okay, so for today, I'm then going to stop the meeting.
Thank you, sir.
Thank you all of you.
Thank you, sir.
Thank you, sir.